Welcome to the Explainer. Today, we're heading out on a massive cosmic safari to explore 18 mind-bending star types pulled directly from our source material. If you've ever looked up at the night sky and wondered what exactly is burning up there in the dark, well, you are in the perfect place. We're going to break down the entire life cycle, the insane variety, and the extreme physics of stars. So get ready, because the universe is far weirder and honestly, way wilder than it looks from down here on Earth.
Here's our roadmap for the journey. First up, we'll tackle the dwarves and main sequence stars. Then we'll scale way up to the giants, supergiants, and hypergiants. After that, things get dark as we enter the stellar graveyard. And finally, we'll push the absolute boundaries of physics with black holes and theoretical stars.
All right, let's kick things off with Section 1, the dwarves and main sequence. We'll be exploring the familiar, incredibly stable stars right in our own cosmic neighborhood.
Now, red dwarfs are brilliantly common. In fact, they make up roughly 75% of all the stars in the universe. Because they're relatively small and cool, sitting somewhere between 2500 and 3500 Kelvin, they sip their hydrogen fuel incredibly slowly. We're talking lifespans of over 1 trillion years. And since the universe itself is only about 13.8 billion years old, it means no red dwarf has actually ever had enough time to die yet. They are literally the quiet, enduring marathon runners of the cosmos.
But what about our own star? Well, our sun is a yellow dwarf, which gives it a lifespan of roughly 10 billion years. But compare that to an orange dwarf. They're about 60 to 80% the mass of our sun, but they live for 15 to 30 billion years. Because they're more stable, produce way fewer dangerous solar flares, and live so much longer, orange dwarfs are actually considered much stronger candidates for hosting habitable planets than our own solar system star. Life simply has way more time to develop.
Then we have a couple of really unique outliers. First, brown dwarfs. These are essentially failed stars. They sit right in that awkward middle ground between the heaviest gas giant planets and the lightest red dwarfs. But they never accumulated quite enough mass to kickstart ordinary hydrogen fusion. So instead, they just weakly fuse deuterium and lithium, cooling down over time. And then you have subdwarfs. These are ancient, dim relics hanging out in the galactic halo. They contain very few heavy elements, which actually tells us they formed very early in the universe's history, back when those heavier elements were super scarce.
Now here's something wild. A blue dwarf? It doesn't actually exist yet. This is a purely theoretical star. As we mentioned earlier, red dwarfs live for trillions of years. But physics predicts that when a red dwarf finally does start running out of hydrogen, instead of puffing up and expanding, its temperature is going to spike and its color will shift entirely from red to blue. Our universe is simply too young for a single red dwarf to have reached this stage. Okay, moving on to Section 2, giants, supergiants, and hypergiants. These are the massive, extremely volatile, and short-lived titans of the cosmos.
The scale of these giants is absolutely terrifying. When a star like our sun finally exhausts its core hydrogen, it expands into a red giant. In about 5 billion years, our sun is going to grow so incredibly large it'll swallow our inner solar system, Mercury, Venus, and possibly even Earth. But honestly, that is nothing compared to a red supergiant. These are the largest stars by volume in the universe. If you took a red supergiant like Betelgeuse and swapped it out with our sun, it would casually swallow everything out to Jupiter.
Out here, the universe operates on a strict live fast, die young rule. Just look at the massive shift in temperature and lifespan compared to the dwarfs. Blue giants and blue supergiants are unbelievably hot, reaching up to 50,000 Kelvin. But they burn through their fuel so aggressively they only stick around for a fleeting few million years before going supernova. And then you have the hypergiants. Take a star like UI Scuti. It's an unstable monster pumping out millions of times more light than our sun. These hypergiants shed mass so rapidly through powerful stellar winds that they are doomed to an incredibly fast, catastrophic death.
And that rapid death brings us to the Wolf-Rayet stars. The creation of these things is insanely violent. In its extreme late evolutionary stage, a highly massive star will literally blow its own outer hydrogen layers off into space using intense stellar winds that reach up to 2,000 kilometers per second. What gets left behind is just the naked, exposed, helium-burning core. This core is blisteringly hot, with surface temperatures sometimes rocketing past 200,000 Kelvin. They are among the absolute hottest stars we have ever discovered.
So what happens after the explosion? Welcome to Section 3, the stellar graveyard, where we look at mind-bending density and the remnants of dead stars.
This is where the physics gets truly bizarre, with a sheer escalation of density.
When average stars die, their cores become white dwarfs, packing the entire mass of the Sun into a sphere no bigger than Earth. Just 1 teaspoon of that material weighs 5.5 tons. But if a really massive star goes supernova, you get a neutron star. This is the collapsed core compressed into a sphere just 20 kilometers across. Going from a white dwarf to a neutron star takes us from super heavy to completely incomprehensible. 1 teaspoon of neutron star material weighs 6 billion tons. The gravity is so immense that electrons and protons are literally crushed together into neutrons.
Now, if a neutron star spins wildly, it becomes what we call a pulsar. Pulsars act like cosmic lighthouses. They emit these sweeping beams of electromagnetic radiation from their magnetic poles. And the rotation is unnervingly precise, literally rivaling atomic clocks here on Earth. In fact, when Jocelyn Bell Burnell discovered the first pulsar back in 1967, the signal was so perfect, so incredibly regular, that researchers actually joked it might be alien communication. They briefly nicknamed the signal LGM-1, which stood for Little Green Men.
1 quadrillion. Just let that number sit with you for a second. That is the strength of a magnetar's magnetic field compared to a typical planetary field, up to a quadrillion times stronger than Earth's. A magnetar is a specialized, intensely magnetic neutron star, and its raw power is almost impossible to grasp. To put that magnetic power into perspective, if you placed a magnetar just halfway to our moon, its magnetic field is so ridiculously strong it would wipe the data off every single credit card on Earth. In 2004, a magnetar called SG-180620 released a massive flare. In just 1/10 of a second, it emitted more energy than our Sun produces in 100,000 years. That single burst was so powerful it physically disturbed Earth's ionosphere from 50,000 light-years away. Incredible. Finally, we arrive at Section 4, Black Holes and Theoretical Stars, the absolute extremes of gravity and high-pressure physics. Let's start with the event horizon. It's the definitive boundary around a black hole beyond which the gravitational force is so overwhelming that absolutely nothing, not even light, can escape. The fascinating thing here is that black holes aren't technically stars themselves. They are the ultimate gravitational tombstone for a massive star, specifically stars that start out with more than 20 solar masses. When they die, gravity just wins completely and crushes the core down infinitely. And these black holes scale dramatically. You have stellar black holes ranging from 5 to a few tens of solar masses, just scattered quietly throughout our galaxy. But then you have supermassive black holes. These are millions to billions of times the mass of our Sun, and they completely dominate the centers of galaxies. For decades, they were totally invisible to us, but in 2019, humanity finally captured the very first image of a black hole, the supermassive beast at the center of galaxy M87, proving they exist visually once and for all.
Finally, we reach the absolute edge of human knowledge, the quark star. These are hypothetical objects sitting right on the knife's edge between a neutron star and a black hole. The idea is that if the pressure inside a neutron star gets extreme enough, the neutrons themselves are crushed and break apart into a dense, ultra-weird soup called quark matter. In 2002, the Chandra X-ray Observatory actually spotted 2 candidates that seemed too small to be neutron stars but too big to be black holes. While they're still purely theoretical, they represent a place where the laws of physics are squeezed so hard that standard matter just breaks down completely.
So, from trillions of years of slow, quiet burning inside red dwarfs to the violent, reality-bending collapse of supernovas, magnetars, and black holes, the universe is so much wilder than we can even imagine. It really makes you wonder, which of these bizarre stellar phenomena will completely redefine our understanding of physics next? Think about the sheer scale of everything we've covered today. Keep looking up, stay curious, and thank you so much for exploring with us on this explainer.